Hello and most welcome to 1077 of the Heidegger series. And today I will address a very important subject. A realization that took a little bit too long, I'd say, but it doesn't make it any less important. I would say even more so. When I was studying philosophy the other year, a repetition of the philosophy studies I made all those years ago. A couple of times during the course, discussion came up and the professor would ask, well, what is the current standing in science? I thought it was, or I think it is, or something similar. And students were asked to find out what was the current standard of science. And that meant that science sort of set the limits to philosophy. It was calling the shots. And this is of course very shocking and means that science comes before anything else. It is the judge what you can say in philosophy. And what sort of science is it? It is of course classical science and nothing else. That I knew, but I now also come to an understanding that that is the case in every academic subject bar none. That is always the case. And this is what I'm going to address today, and that is that it is not a minor problem that classical physics is deciding what is true or what is not true, or in which format all discourse should take, and even the goal of the subjects today. There is a pretty good shot, I won't say it, but it's a pretty good shot to say that this could be the reason for the closing of the Western mind. An incorrect science is doing a lot of influence within subjects where it doesn't even is supposed to be. I can say directly offhand that sociology, psychology, anthropology, ethnology, archaeology, all those subjects are incredibly influenced by classical physics. And since classical physics is incorrect, it doesn't work, it's been discarded to some way, it means that a false dichotomy is being established. And the dichotomy there where we are outside of reality and that consciousness is something of a translucent non-material thing somewhere bystander to all of reality, not part of it. This is the idea of an inert universe, and of course it means also that these false dichotomies between truth and untruth are made to take over what is not their domain at all, and replace knowledge, understanding with simple childish-like dichotomies. I think this attack calls for a puff on my pipe. I don't see how it would work. I would like to, in this lecture, include something that came to fore in a course in quantum mechanics. And that was an example that sort of extrapolated some insight from Wigner. It's an experiment designed by Daniela Frauchiger and Renner of the Swiss Federal Institute of Technology in Zurich. And it involves a set of assumptions that on the face of it seems entirely reasonable. But the experiment leads to contradictions, suggesting that at least one of the assumptions is wrong. The choice of which assumptions to give up has implication for our understanding of the quantum world, and points to the possibility that quantum mechanics is not a universal theory and so cannot be applied to complex systems such as humans. Quantum physicists are notoriously divided when it comes to the correct interpretation of the equations that are used to describe quantum goings-on. But the new thought experiment, no view of quantum world comes through unscathed. Each one falls afoul of one or another assumption. Could something entirely new await us in search for an uncontroversial description of reality? And I think that last sentence is very important, because what is limiting current thought is the idea of a clear view of the world. That is a possibility. It's something that underpins all subjects of academia today. And since this is a rather new concept, at least in subjects outside of physics, since at least the mid-19th century, I think that makes the evidence huge that it is classical physics with its inherent idea of one uncontroversial description of reality so clear. We have found our culprit, or elementary dear Watson, as Sherlock Holmes would have said. And I remember more and more how many professors were talking about an outside world or reality and such stuff. Objective truth, it's a proven fact, and so forth and so forth. I can imagine you who are seeing this or listening to this recall such instances as well, and of course that you have been thinking it as well. It is very ingrained in today's society. Well, let's continue with the quantum theory, and this would be very good also to link to if you want to have a somewhat more understandable experiment of quantum mechanics. Now let me continue. Quantum theory works extremely well at the scale of photons, electrons, atoms, molecules, even macromolecules. But is it possible to transport all of these weird effects to the macro level of human beings? And in this case, Renner said, in particular, we don't know whether it extends to objects the size of humans or even lesser. It extends even lesser, whether it extends to objects the size of black holes. And this is an extension, as I mentioned, something that the physicist, the well-renowned Eugene Wigner, first dreamt up in the early 60s. The new experiment shows that in a quantum world, two people can end up disagreeing about a seemingly irrefutable result, such as the outcome of a coin toss, suggesting something is amiss with the assumptions we make about quantum reality, or for that case, any reality. In standard quantum mechanics, a quantum system such as subatomic particles is represented by mathematical abstraction called the wave function. Physicists calculate how the particle's wave function evolves with time. But the wave function does not give us the exact value for any of the particle's properties, such as its position. If we want to know where the particle is, the wave function's value at any point in space and time only let us calculate the probability of finding the particle at that point. Should we choose to look? Before we look though, the wave function is spread out and it encodes different probabilities for the particle being in different places. The particle is said to be in a quantum superposition of being in many places at once. More generally, a quantum system can be in a superposition of states where state can refer to other properties such as the spin of a particle. Much of the Frauchiger-Renner thought experiment involves manipulating complex quantum objects, maybe even humans, that end up in superpositions of states. The experiment has 4 agents: Alice, Alice's friend, Bob, and Bob's friend. 4 people. Alice's friend is inside a lab making measurements on a quantum system, and Alice is outside monitoring both the lab and her friend. Bob's friend is similarly inside another lab, and Bob is observing his friend and the lab, treating them both as one system. Inside the first lab, Alice's friend makes a measurement on what is effectively a coin toss, designed to come up heads 1/3 of the time and tails 2/3 of the time. If the toss comes up heads, Alice's friend prepares a particle with a spin pointing down, but if the toss comes up tails, she prepares a particle in a superposition of equal parts, spin up and spin down. Alice's friend sends the particle to Bob's friend, who measures the spin of the particle. Based on the result, Bob's friend can now make an assertion about what Alice's friend saw in her coin toss. If he finds the particle spin to be up, for example, he knows the coin came up tails. The experiment continues. Alice measures the state of her friend and her lab, treating all of it as one quantum system, and uses quantum theory to make predictions. Bob does the same with his friend and lab. Here comes the first assumption. An agent can analyze another system, even a complex one, including other agents using quantum mechanics. In other words, quantum theory is universal, and everything in the universe, including entire laboratories and the scientists inside them, follow the rules of quantum mechanics. This assumption allows Alice to treat her friend and the lab as one system and make a special type of measurement which puts the entire lab, including its contents, into a superposition of states. This is not a simple measurement, and herein lays the thought experiment's weirdness. The process is best understood by considering it as a single photon that's in a superposition of being polarized horizontally and vertically. Say you measure the polarization and find it to be vertically polarized. Now, if you keep checking to see if the photon is vertically polarized, you will always find that it is. But if you measure the vertically polarized photon to see if it's polarized in a different direction, say at a 45-degree angle to the vertical, you'll find that there is a 50% chance that it is, and a 50% chance that it isn't. Now if you go back to measure what you thought was a vertically polarized photon, you will find that there is a chance that there is no longer vertically polarized at all. Rather, it's become horizontally polarized. The 45-degree measurement has put the photon back into superposition of being polarized horizontally and vertically. This is all very fine for a single particle, and such measurements have been amply verified in actual experiments. But in the thought experiment, Frauchiger and Renner want to do something similar with complex systems. At this very stage in the experiment, Alice's friend has already seen the coin coming up either heads or tails. But Alice's complex measurement puts the lab, friend included, into a superposition of having seen heads and tails. Given this weird state, it's just as well that the experiment does not demand anything further of Alice's friend. Alice, however, is not done. Based on her complex measurement, which can come out as either yes or no, she can infer the result of the measurement made by Bob's friend. Say Alice got yes for an answer, she can deduce using quantum mechanics that Bob's friend must have found the particle's spin to be up, and therefore that Alice's friend got tails on her coin toss. This assertion by Alice's necessitates another assumption about her use of quantum theory. Not only does she reason about what she knows, but she reasons about how Bob's friend used quantum theory to arrive at his conclusion about the result of the coin toss. Alice makes that conclusion her own. This assumption of consistency argues that the prediction made by different agents using quantum theory are not contradictory. Meanwhile, now it starts, Bob can make a similarly complex measurement on his friend and his lab, placing them in a quantum superposition. The answer can again be yes or no. If Bob gets yes, the measurement is designed to let him conclude that Alice's friend must have seen heads in her coin toss. It is clear that Alice and Bob can make measurements and compare their assertions about the results of the coin toss. But this involves another assumption. If an agent's measurement says that the coin toss came up heads, then the opposite fact that the coin toss came up tails cannot be simultaneously true. This is why we have a coin toss, because it only has two excluding answers. The setup is now ripe for a contradiction. When Alice gets a yes for her measurement, she infers that the coin toss came up tails, and when Bob gets a yes for his measurement, he infers that the coin toss came up heads. Most of the time, Alice and Bob will get opposite answers, but Frauchiger-Renner show that in 1/12 of the cases, both Alice and Bob will get a yes in the same run of the experiment, causing them to disagree about whether Alice's friend got a heads or a tails. So both of them are talking about the past event, and they're both sure what it was, but the statements are exactly opposite. Renner said, and that's the contradiction. That shows something must be wrong. This led Frauchiger and Renner to claim that one of the three assumptions that underpin the thought experiment must be incorrect. Renner said, the science stops here. We just know one of the three is wrong, and we cannot really give a good argument as to which one is violated, Renner said. This is now a matter of interpretation and taste. Fortunately, there are a wealth of interpretation of quantum mechanics, and almost all of them have to do with what happens to the wave function upon measurement. Take a particle's position. Before measurement, we can only talk in terms of the probabilities of, say, finding the particle somewhere. Upon measurement, the particle assumes a definite location. In the Copenhagen interpretation, measurement causes the wave function to collapse, and we cannot talk of properties such as particle's position before collapse. Some physicists view the Copenhagen interpretation as an argument that properties are not real until measured. This form of anti-realism was an anathema to Einstein, as it is to some quantum physicists today. And so is the notion of a measurement causing the collapse of the wave function, particularly because the Copenhagen interpretation is unclear about exactly what constitutes a measurement. Alternative interpretations or theories mainly try to either advance a realist view that quantum systems have properties independent of observers and measurements, or avoid a measurement-induced collapse, or both. For example, the many worlds interpretation takes the evolution of the wave function at face value and denies that it ever collapses. If a quantum coin toss can be either heads or tails, then in the many worlds scenario both outcomes happen, each in a different world. Given this, the assumption that there is only one outcome for a measurement, and that if the coin toss is heads, it cannot simultaneously be tails, become untenable. In many worlds, the result of the coin toss is both heads and tails. And thus the fact that Alice and Bob can sometimes get opposite answer is not a contradiction. If you had to admit that if you had asked me 2 years ago, I'd have said our experiment just shows that many worlds is actually a good interpretation, and you should give up the requirement that measurement have only one single outcome, Renner said. This is also the view of the theoretical physicist David Deutsch of the University of Oxford, who became aware of the Frauchiger-Renner paper when it first appeared on Archive X. In that version of the paper, the authors favor the many worlds scenario. Deutsch thinks that the thought experiment will continue to support many worlds. He says, my take is likely to be that it kills wave function collapse or single universe versions of quantum theory, but they were already stone dead, he said. Yes, good of Deutsch. I am not sure what purpose it serves to attack them again with bigger weapons. And this is interesting. Renner, however, has changed his mind. He thinks the assumption most likely to be invalid is the idea that quantum mechanics is universally applicable. This assumption is violated, for example, by so-called spontaneous collapse theories that argue, as for the name suggests, for a spontaneous and random collapse of the wave function, but one that is independent of measurement. These models ensure that small quantum systems such as particles can remain in superposition of states almost forever. But as system gets more massive, it gets more and more likely that they will spontaneously collapse to the classical state. Measurements merely discover the state of the collapsed system. In spontaneous collapse theories, quantum mechanics can no longer to be applied to systems larger than some threshold mass. And while these models have yet to be empirically verified, they haven't been ruled out either. Nicolas Gisin of the University of Geneva favors spontaneous collapse theory as a way to resolve the contradiction in the Frauchiger-Renner experiment. My way out of the conundrum, he says, is clearly by saying no at some point. The superposition principle no longer holds, he said. And this is from Renato Renner. We have not experimentally established the fact that quantum mechanics applies on larger scales, and larger means even something the size of a virus or a little cell. This is something from Renato Renner. If you want to hold on to the assumption that quantum theory is universally applicable and that measurements have only a single outcome, then you've got to let go of the remaining assumption, that of consistency. The predictions made by different agents using quantum theory will not be contradictory. Using a slightly altered version of the Frauchiger-Renner experiment, Leifer has shown that this final assumption, or a variant thereof, must go if Copenhagen-style theories hold true. In Leifer's analysis, these theories share certain attributes, in that they are universally applicable, anti-realistic, meaning that quantum systems don't have well-defined properties such as position before measurement, and complete, meaning that there is no hidden reality that the theory is failing to capture. Given these attributes, his work implies that there is no single outcome of a given measurement that's objectively true for all observers. So he continues, Leifer, if you want to maintain the Copenhagen type of view, it seems the best move towards this perspective version, Leifer said. He points out that certain interpretations such as quantum Bayesianism or QBism have already adopted the stance that measurements outcomes are subjective to an observer. So what he says is, given these attributes, his work implies, Leifer, that there is no single outcome of a given measurement that's objectively true for all observers. So if a detector clicked for Alice's friend inside the lab, then it's an objective fact for her, but not so for Alice, who is outside the lab modeling the entire lab using quantum theory. The results of measurements depend on the perspective of the observer. Renner is not so happy with Leifer. I can tell you I am, but Renner isn't. Renner thinks that giving up this assumption entirely would destroy a theory's ability to be effective as a means for agents to know about each other's state of knowledge. Such a theory could be dismissed as solipsistic. So any theory that moves towards facts being subjective has to establish some means of communicating knowledge that satisfies two opposing constraints. First, it has to be weak enough that it doesn't provoke the paradox seen in the Frauchiger-Renner experiment, yet it must also be strong enough to avoid charges of solipsism. No one yet has formulated such a theory to everyone's satisfaction. The Frauchiger-Renner experiment generates contradictions among a set of three seemingly sensible assumptions. The effort to explicate how various interpretations of quantum theory violate the assumption has been an extremely useful exercise, said Rob Spekkens, with 2 Ks, of the Perimeter Institute for Theoretical Physics in Waterloo, Canada. He says, this thought experiment is a great lens through which to examine the differences of opinions between different camps on the interpretation of quantum theory. Spekkens said, I don't think it's really eliminated options that people were endorsing prior to the work, but it has clarified precisely what the different interpretational camps need to believe to avoid this contradiction. It has served to clarify people's positions on some of these issues. Given that theoreticians cannot tell the interpretations apart, experimentalists are thinking about how to implement the thought experiment in hope of further illuminating the problem. But it will be a formidable task, because the experiment makes some weird demands. For example, when Alice makes a special measurement on her friend and her lab, it puts everything, the friend's brain included, into superposition of states. Mathematically, this complicated measurement is the same as first reversing the time evolution of the system, such that the memory of the agent is erased and the quantum system, such as the particle the agent has measured, is brought back to its original state, and then performing a simpler measurement on just the particle, said Howard Wiseman of Griffith University in Brisbane, Australia. The measurement may be simple, but as Gisin points out rather diplomatically, reversing an agent including the brain and the memory of that agent is a delicate part, yes, so to say. Nonetheless, Gisin is not averse to thinking that maybe one day the experiment could be done using complex quantum computers as the agents inside the labs, acting as Alice's friend and Bob's friend. In principle, the time evolution of a quantum computer can be reversed. One possibility is that such an experiment will replicate the predictions of standard quantum mechanics, even as quantum computers get more and more complex. But it may not. Another alternative is that at some point, while we develop these quantum computers, we hit the boundary of the superposition principle and find that actually quantum mechanics is not universal, Gisin said. Leifer, for his part, is holding out for something new. I think the correct interpretation of quantum mechanics is none of the above, he said. He likens the current situation with quantum mechanics to the time before Einstein came up with his special theory of relativity. Experimentalists had found no sign of the luminiferous ether, the medium through which light waves were thought to propagate in a Newtonian universe. Einstein argued that there is no ether. Instead, he showed that space and time are malleable. Pre-Einstein, I couldn't have told you that it was the structure of space and time that was going to change, Leifer said. Quantum mechanics is in a similar situation now, he thinks. Quote, it's likely that we are making some implicit assumption about the way the world has to be. That just isn't true, he said. Once we change that, once we modify that assumption, everything would suddenly fall into place. That's kind of the hope. Anybody who is skeptical of all interpretation of quantum mechanics must be thinking something like this. Can I tell you what's a plausible candidate for such an assumption? Well, if I could, I would just be working on that theory, he says. Well, obviously this flies into the eyes of an idea of a exhaustible world that can be exhaustively described. None of the propositions solves that problem, and if you don't want to accept many worlds, which I say would be a defeat. So that shows that the general tendency in all academia today, a new tendency, no older than at the oldest 1850s, but in some subjects it's much younger. In literature theory it doesn't sort of mingles in before 50s, 60s, I'd say. They all have the idea of one unified world where all see the same thing, same reality, the same coin toss. There are none in this world, no one in this world, in the Western Hemisphere, who doesn't consider that as well, I would be brave to say. Contradictions are not accepted by anyone on the everyday situation. That is not an accepted stance. You would be admitted to the hospital quite quickly. And this goes to show, I'd say, for the absolute necessity for quantum mechanics as an antidote, as a pharmacon. And in this case, it's a pharmacon that has a dual effect. It's both poison and medicine. Needs to be. Will poison our worldview? Yes. But it will heal ourselves. It will heal the assumption that we are not part of the world, that we are bystanders looking at the world. And obviously this points to the Heideggerian project having both untrue and truth is a necessity if we have a perspective world where different people have different objective truths. It's the Necky cube all over. And Heidi tries to help us get rid of the idea of one objective world in that sense, without an observer. Observer plus world makes a world. Observer is always in the world and always have been. Cannot be excluded from the world, would never be a possibility. And assuming that will rid us of the possibility of understanding, of knowledge. I think all these things are incredibly necessary today. They are a pharmacon, they're an antidote to the bystander assumption, if it's even is an assumption. Because it's like a straitjacket, the idea of one objective world out there where observers are not important, not taking any part. It is a killer of all things. So pharmacon, that is what quantum mechanics is. And in the Frauchiger-Renner experiment, it is even clearer that people striving to continue with the one world, it's just beyond me. I don't know why many words come up. Trying to preserve something that is obviously dated, no longer a valid part of the explanatory physics. And those nerds like you, Everett, or Max Tegmark, they are obviously not of this world. They are like those extreme examples of Daniel Dennett, not part of the world, having no free will or anything like that. And this will heal the world because we are having a wound. Of course, assuming we're not part of the world, or this general gestalt of not being more than observers to our all thinking reality, rids us of the closeness, make everything distant. And no wonder modern academia, in contrast to old academia, is cold. It doesn't have any sentiment, it doesn't have a heart anymore. And that coldness is, for some mad reason, something you should imitate. Listen to, I think it was 2 years ago, when I was staying in Jonsered, to some lecture by some lecturer. They tried to sound as uninteresting as possible to get the impression of being objective or something. How ridiculous. Like his own passion would kill off the truth of his own words. It is just the opposites. Lacking passion is a killer of words. I can also see the same tendency in journalists in Sweden, trying to look as goddamn serious as it is actually possible. What is the reason? Well, when you are transmitting the objective truth coming from nowhere, you should not be emotionally engaged, or you should pretend to be non-emotionally engaged by looking like half angry. That's my objective look. This is how I look when I say objective stuff. I can't even imitate. Then I'm no longer in my body. I cannot laugh at anything, I can't get angered, I can't get happy, I can't get engaged, I can't get curious. Nothing human. Just trying to rid myself of all humanity in order to be objective. That is indeed ridiculous. And classical physics is ridiculous, even though it can all be explained by quantum mechanics. And quantum mechanics shows that classical physics idea of one world is dead born. It was dead already before it was born. so it wasn't even stillborn. I say thank you very much, and I think I end here. I say if I can put links to all these interesting scientists and the different views. This goes to show that an open experiment like this has a great deal more power than an experiment that in a single way shows one truth only. This one puts more question in than it answers, and therefore it's so fantastic. I say thank you very much and have a very pleasant afternoon. Bye bye for now.